Now that we covered the basic concepts of circuit analysis in the previous video, we can start to figure out how to solve for values in our circuits using Ohm's law and Kirchhoff's laws. Imagine you have a piece of copper and a piece of glass and they have the same shape and size. If we apply the same voltage between the ends and measure the current that flows through them, we get two different values. That's because the glass has a much higher resistance than the copper. When we have a circuit that requires a certain resistance, we use something called a resistor to do that. In simple terms, they are just conductors, so a material that allows electricity to flow with a specified resistance. On a circuit diagram, they are represented by this symbol. In real life, they look like this. Some have color bands on them which tells you the resistance, and others have digits on them to convey the same information. A physicist by the name of George Simon Ohm figured out that there is a relationship between voltage, current, and resistance, and that relationship is called Ohm's law. It's a great tool to use when analyzing circuits. If we rearrange this equation for current, we see that the higher the resistance, the lower the current will be. Resistance is measured in ohms, with the capital Greek letter omega as its symbol. 1 ohm is equal to 1 volt per ampere. By knowing two of the variables, we can figure out the third. So here, we see a voltage source with 5 volts, and there is a resistor that has a value of 10 ohms. We can directly solve for the current flowing through the resistor using Ohm's law. You might have seen this triangle before, so keep it in mind when you quickly need to solve for current, resistance, or voltage. By covering what you want to find, you get the equation you need. So if you want current, you cover I and you see that it's V over R and so forth. Here's another circuit where we can easily make a mistake. Notice we have two resistors in this circuit with a single voltage source. You cannot apply Ohm's law to each resistor using the same voltage. In the next video, we will cover how the voltage in a series circuit is different for each element. But for now, keep in mind that Ohm's law works when you know the resistance, current, or voltage directly at that element. In other words, we need to know the voltage of each resistor, or the current passing through each resistor. Remember from the previous video that power was equal to voltage times the current. Using what we learned right now, we can express power as a function of resistance and current, and a function of resistance and voltage just by plugging in Ohm's law isolated for current and isolated for voltage. There are two scenarios you need to keep in mind when it comes to resistance. That is when resistance is 0 and when it approaches infinity. Here is a simple circuit. If we decrease our resistance, making it smaller and smaller, at some point our resistance will be 0, and the circuit is a short circuit. So our diagram can look like this. In this case, the voltage is 0, though the current can be any value. On the other hand, if we increase the resistance, making it larger and larger, at some point our circuit becomes an open circuit and would look like this. In simple terms, there is no flow of current anymore, so current is 0. The reciprocal of resistance is called conductance. It's represented with a capital letter G and it's equal to 1 over R, or current divided by the voltage. The unit for conductance is called a Siemens, and 1 Siemens is equal to 1 ampere per voltage. We can also express power with conductance as well, like this. Just as Ohm's law is useful in analyzing circuits, another set of laws called Kirchhoff's laws are equally important. But before that, we need to discuss a few basic things about a circuit. Here is a big circuit. These black lines are called conductors, and we assume them to be perfect. In simple terms, these wires have 0 resistance, which means the energy in the circuit is in each element. These points here are called nodes. It's a point of connection of 2 or more circuit elements. Assume we start from this point and keep moving until we reach this resistor here. The path we covered is a single node. Here's another node. Notice how the entire bottom of this circuit is a single node. In simple terms, a node is one end of a circuit element that have conductors attached to it. Now if you look, you can see many different paths in this circuit. A loop is a closed path where a node is not encountered more than once. So here are some loops. Here is something that is not a loop. Notice how this makes it so that node 5 is encountered twice. Lastly, a branch is a segment of a circuit containing a single element, and there are nodes at each end of the element. So in this circuit, there are 8 branches. Now we can move on to the first Kirchhoff law, which is called Kirchhoff's current law, KCL for short. It states that the algebraic sum of currents entering any node is 0. So going back to our circuit, let's focus on node 2. Here we have I3 entering, I5 entering, and I4 leaving. Current entering will be considered positive, and current leaving the node will be considered negative. You can assume the opposite and you will still end up with the same answers. Using KCL, we can say that I3 plus I5 minus I4 is equal to 0. Another way of thinking about this is to realize that the sum of currents entering a node must equal the sum of currents leaving a node. The second Kirchhoff's law is called Kirchhoff's voltage law, KVL for short. It says that the algebraic sum of voltages around any loop is 0. So here is a simple circuit. When doing KVL for a loop, you can traverse a circuit in either clockwise or counterclockwise direction. You will end up with the same answer. So starting here, we will go clockwise. We encounter a positive 6 volts, then positive 8 volts, then positive 4 volts, and lastly, we see that we enter the negative side of this power source, so a negative 18 volts. Adding all of this together gives us 0 volts. Sometimes, questions will ask you to find the voltages between 2 arbitrary points, and the notation will look like this. So in this circuit, we need to find the voltage between these 2 points. Note that in this notation, the first subscript is considered positive relative to the second subscript. So point A is positive compared to point B. Another way of showing this is to use an arrow. The head of the arrow points to the first subscript in the written notation. So remember, we assume this side to be positive since that's where the head of the arrow is. Now we can write a KVL for this loop, assuming VAB to be an unknown variable. The loop you want to use is completely up to you. I will use 2 loops to show that you get the same answer. Let's go clockwise in this loop. Now we can do this loop. Notice how when we went clockwise for this loop, we entered the negative side of VAB and we get the same answer. Now let's move on to some examples to see how to apply what we learned. We can start with an easy one. We just need to figure out the current and power dissipated in the resistor. Using Ohm's law, we can figure out the current flowing in this circuit. The voltage is 9 volts and the resistance is 12 ohms. So we get a current flow of 0.75 amps. To find power, we use P equals VI. Let's solve, and that's our answer. Let's look at another one. We are told that the resistor in this circuit absorbs 20 milliwatts of power. We need to figure out the resistance value. We can directly solve for resistance using our power equation. This is just the power equation and Ohm's law combined. Remember to convert milliwatts and milliamps. Let's take a look at this example where we need to find I1 and I2. For that, we can use KCL. So let's label this node 1 and this node 2. Looking at node 1, we have I1 entering and then we have 2 currents leaving. We will assume currents coming into the node to be positive while those leaving to be negative. So let's write our KCL. We can solve for I1. Next, let's look at node 2. We have 1 current entering and 2 leaving. Let's solve for I2, and those are our answers. Let's take a look at this circuit where we need to find I1, I2, and I3. Let's start by labeling our nodes. We will need to write a KCL equation for each node and then solve the equations. Let's start with node 1. We have 12 milliamperes coming in and IX and I3 leaving. Next, we have node 2, and we go on like this for all 5 of the nodes. Now you can solve the equations any way you like, substitution, elimination, whatever you're comfortable with, but if you like to see how it was solved, please see the description of the video. We get these values for our currents, and those are our answers. The negative signs indicate that the directions given for the currents were opposite to what they really are. Let's take a look at this question where we need to find the voltage between points A and D. Note the subscript. A is the first letter, so point A is going to be considered positive relative to point D. We can draw an arrow like this, with the head of the arrow pointing at A, and that side will be the positive side. Now we can write a KVL for any loop involving AD. We will pick the big loop and go clockwise. Let's solve and we get 7 volts. Let's take a look at this problem where we need to find Vx and Vy. Using KVL and this loop here, we can figure out Vy. To figure out Vx, we can use this loop and write our KVL equation. And those are our answers. Let's take a look at this question where we need to find V1, V2, and V3. For V1, we can write a KVL for this loop. Let's go clockwise. Next, we need to figure out Vx because that will be helpful for the other loops. So let's write a KVL equation for this loop. Now that we have Vx, we can write a KVL for this loop to figure out V2. Let's plug in the value of Vx and solve for V2. Now we can write another KVL for this loop to figure out V3. Let's solve, and those are our answers. That should cover the types of problems you will face when it comes to Ohm's law and Kirchhoff's laws. Thanks for watching, and best of luck with your studies.